grab your phone for a second and just, look at it.
Yeah, the little supercomputer we all carry around.
Exactly. Because if you think about it, the audio processor inside that device is performing like millions of perfectly timed, pristine mathematical calculations right now, just so you can hear my voice.
Right, it's a completely sealed off, perfect environment.
It is the absolute pinnacle of engineering control. The ones and zeros stream flawlessly. They catch every nuance. They filter out every error.
Yeah.
We have basically engineered our world so that our technology does perfectly and predictably exactly what we tell it to do.
Which is great for phone calls, but we've effectively banished the ghost from the machine,
Yeah.
Digital audio is designed to be this sterile place where accidents just simply cannot happen.
But what happens when you decide to break that seal? Like, what happens when you rip those exact same perfect microchips out of their natural habitat?
Oh, it gets messy.
Right. You starve them of electricity, you wire them up backwards, and you basically force them to scream. You end up stepping into a musical landscape that is just completely unhinged.
Yeah, you find yourself in the absolute definition of raw, untamed electronic chaos.
Welcome to the Deep Dive. Today we are taking you into this forgotten, beautifully primitive corner of electronic music. We're exploring a really fascinating column from MMR, and it uncovers this underground culture of CMOS synths and the incredibly strange Lunetta community.
It is such a weird and wonderful world.
It really is. And our mission today is to figure out how raw computer logic, chips like little pieces of silicon, originally designed for really boring industrial math calculations, how they're being hacked to create this wild, unpredictable music.
And maybe more importantly, why a DIY movement like this actually matters to you in our modern world of, hyper-polished software. Because the irony at the center of all this is really what makes it so compelling. I mean, the fundamental logic chips that eventually paved the way for our pristine digital world, they're being dragged out of their intended context and used to generate filthy, unpredictable noise.
Okay, let's unpack this, because I really want to deliver a massive aha moment for you today about how rigid mathematics can literally be twisted into a living, breathing instrument.
Yeah, let's do it.
But before we get to the wild sounds, we really need to establish what a CMOS synth actually is. Because, you hear the word synth and you probably picture like a keyboard on a stand with a bunch of presets.
Yeah, maybe a pitch bend wheel, some sliders.
Exactly. But that is not what we're dealing with here at all, is it?
Not even close.
No.
So CMOS logic chips are those tiny, unassuming black rectangles with the little metal legs, the ones you see soldered onto green circuit boards.
Right, the classic computer chip look.
Exactly. And they were designed for signal processing, industrial machine timing, basic true or false logic operations in early computers. They are meant to count, to sort, and to make binary decisions. They were never, ever designed to produce audio.
And that brings us to the Lunetta synth, which is this specific subculture named after an Italian-American DIY builder and sculptor. His name was Stanley Lunetta.
Stanley was a pioneer, yeah.
Yeah, he really was. And he had a very specific philosophy. He laid down these incredibly strict rules for what makes a true Lunetta synth. The system must consist exclusively of these basic CMOS logic chips.
Right, no cheating allowed.
Exactly. You cannot use traditional synthesizer parts. So that means no standard analog filters to sculpt the tone, and absolutely no VCAs, which are voltage-controlled amplifiers.
And VCAs are usually components that control volume and make a note, like fade out nicely.
Right, so if you don't have those, it's like you try to build a delicate emotional violin, but your only materials are, I don't know, copper wires and plastic cooling fans from an old motherboard.
That is a great way to picture it. By removing all those traditional tools that make a synthesizer sound conventionally musical, you're left with these really severe constraints.
So if these things have no traditional filters and no traditional amplifiers, does the raw, naked circuit itself basically become the instrument?
What's fascinating here is that, yes, absolutely. That constraint forces a massive philosophical shift in how you even approach making sound. The limitations of using nothing but logic chips birthed this entirely unique sonic signature.
Because you aren't just pressing a key.
No, you aren't playing notes on a keyboard at all. You are physically patching together the flow of electricity, and you are quite literally listening to the machine think. You just take these naked logic chips, you wire them up freely by plugging cables directly between their input and output pins, and you let the tone shift based entirely on how you manipulate the main power supply.
Which is wild because, okay, I understand how a guitar string vibrates to make a sound, right? You pluck it, it physically moves the air, and we hear a note.
For sure, simple physics.
But here we are dealing with a rigid calculator chip. There are 0 moving parts. So how are we actually getting a physical, audible sound wave out of true and false math?
So it all starts with a specific component called a CMOS inverter. If you're looking at a part schematic, it's often called the 4106 chip. And in digital logic, an inverter has one very simple job. It takes an incoming electrical signal and it just flips it.
Right.
So if a signal comes in true, it outputs false. If it receives a high voltage, it immediately outputs a low voltage.
Okay, so Stanley, Lunetta, and this whole DIY community, they realized they could trick the chip.
They did.
They take that output and they wire it directly back into the input. But, and this is the clever part, they place a resistor and a capacitor right in the middle of that loop. And a capacitor basically acts like a tiny bucket filling up with electricity.
That bucket analogy is perfect for understanding the physics here.
Right, so the bucket fills up with voltage. And once it is completely full, it dumps that voltage back into the input of the inverted chip.
Yep.
So the chip sees this high voltage, does its job, and flips the output to low. But because the output is now low, the bucket empties out. And when the bucket is empty, it sends a low signal to the input, so the chip says, oh, I need to flip the output back to high.
Exactly, which starts filling the bucket all over again.
Right, so the chip just gets trapped in this perpetual cycle of confusion, right? It's just filling and dumping, switching from true to false thousands of times every single second.
And that endless, rapid electrical flipping is what we call a self-oscillating loop. In the world of audio, an electrical signal flipping instantaneously between a high voltage state and a low voltage state that creates a square wave.
Wow.
You have just forced a math equation to vibrate the air.
That is incredible. But a single, endless, droning square wave isn't exactly a song, is it?
No, it would get pretty annoying pretty fast.
Right, so to make actual music, they throw other logic chips into the mix. Like, the community relies heavily on counter chips, the 4040 binary counter or the 4017 decade counter. And these chips have a really fascinating function. They literally divide time.
They do. They take that initial incredibly fast square wave, which, by the way, might be oscillating so frantically that the pitch is way above the range of human hearing, and they perform division on it.
Like actual math division.
Exactly. The counter chip basically says, I am only going to send out a pulse every second time I receive a pulse. It literally chops the frequency in half.
And dropping a frequency in half drops the pitch down by exactly 1 octave.
Yep.
So you chain another divider, it cuts in half again, dropping it another octave.
Yeah.
Suddenly, from this one invisible, ultra-fast clock, you have all these different slower rhythms and deep pseudo-melodies just tumbling down into the audible range.
It generates these massive overlapping polyrhythms. It's beautiful in a very structural way.
Okay, here's where it gets really interesting, though, the logic gates. So the sound generation isn't analog synthesis at all. It is literally just Boolean logic operations, like A and D or XOR, just smashing into each other.
Yes, this is where the character really comes from.
I was trying to visualize this for you, the listener, and I realized logic gates are basically like bouncers at a nightclub.
Oh, I like this. Let's follow that logic.
Okay, so imagine your different audio pulses are people trying to get into the club. The A&D gate is the strictest bouncer on the block. He says, I will only open the door and let a sound through if signal A and signal B show up at the exact same millisecond.
Right, they have to be together.
Exactly.
Yeah.
If only one shows up, nothing gets through. And this creates these highly rhythmic, gated, stuttering sound patterns.
Very staccato.
Then you have the OR gate. This bouncer's super chill. He says, I'll let you in if A is here, or if B is here, or if both of you are here.
Yeah, everyone gets in.
Right, so the club gets packed. And your sound becomes this incredibly dense, continuous layer of noise.
But the most dramatic transformations definitely happen with the XOR gate, the exclusive OR.
Yes. The XOR bouncer is a total agent of chaos. He only lets a signal through if A is there or B is there, but never if they arrive together.
Right. No couples allowed.
Exactly. If they both show up at the same time, he just kicks them both out.
Yeah.
It forces the electrical signals to literally collide, cancel each other out, and fracture. It spits out these wild overtones and harsh, grating metallic textures.
And that mechanism right there really reveals the core philosophy of the Lunetta system. Music in a CMOS synth is completely extracted. It's not composed.
Right. You aren't writing a melody.
No, you aren't writing sheet music. You are setting up a hierarchy of high-frequency clocks, dividing them down like fractions, and then routing them through these logic bouncers until our ears perceive the resulting mathematical collisions as rhythm and pitch.
It's just wild.
Yeah.
Now, you'd think that since this is all based on rigid math and logic gates, the resulting sound would be perfectly tight, robotic, and locked to a perfect grid.
You would think that, yeah.
But the reality is the complete opposite. The actual sound of Lunetta Synth is shockingly unstable.
Oh, totally. Because the fundamental building block is that square wave, which is already harmonically aggressive. It sounds very harsh and biting. But the real chaos comes from the fact that these raw CMOS circuits are hypersensitive to their environment.
Because there's no protection, right?
Exactly. Because you stripped away all the stabilizing analog components that a commercial synthesizer uses to keep picks steady, these raw chips are entirely vulnerable.
They react to literally everything, like and changing the room temperature shifts the pitch. Even the physical proximity of two jumper wires just touching each other on the breadboard can cause crosstalk that makes the whole circuit glitch out.
The timing is constantly drifting. The result is this stream of non-periodic patterns that a human could never perfectly program into a computer software grid.
Right.
The music made this way is intensely ephemeral. You could wire up a patch, play an incredible 10-minute set of rhythmic noise, and you will never, ever be able to recreate those exact sounds again, even if you leave all the cables in the exact same spot.
And the biggest wild card in all that chaos has to be the voltage parameter, because these chips are designed to operate anywhere between 3 volts and 15 volts of electricity.
Like, that's their operating window.
And in a normal computer, you want a perfectly steady, unchanging voltage so the chip functions flawlessly. But in a Lunetta Synth, you use voltage as your main playground.
It becomes a performance tool.
Right. If you pump the power up to 15 volts, the chip runs incredibly fast, spitting out this frantic, high-pitched chattering. But if you drop the voltage down near 3 volts, it's like depriving the chips of oxygen.
If we connect this to the bigger picture, we have to look at the physics of the transistors inside the chip to really understand why that happens.
Okay, break that down for us.
A transistor needs a specific threshold of electrical pressure, which is what voltage is, to switch its gate open and closed cleanly. When you drop the power supply down to 3 volts, you are literally starving the circuit.
Wow.
The electrical pressure is so weak that the electrons physically struggle to cross the transistor gap in time.
So the chip is trying to do the math, but its brain is basically operating in slow motion. The electrical gates are opening so sluggishly.
The logic gets completely confused. The crisp, clean, square waves start to round off and deform. What you hear on the other end is this slow, sludge-like, heavily distorted groan. You are literally listening to a microchip struggling to stay awake.
It's like it's falling asleep at the wheel.
Yeah.
That completely forces you to rethink what an instrument even is. You're actually playing the struggle of the circuit.
Breaking the stability is exactly what gives it musicality.
It really makes me wonder about the timeline of all this, because you'd think an instrument this volatile, this difficult to tune or reproduce would just be like a forgotten failed experiment in some engineer's basement.
Well, for a long time, it essentially was. The timeline here kind of mirrors the history of commercial synthesizers, acting as a sort of shadow history.
Right.
In the 1970s, CMOS chips began to spread globally simply because they were cheap, they were reliable for industrial use, and they consumed very little power. Early pioneers experimented with them, sure, but it remained a highly obscure fringe activity.
That makes total sense, because by the 1980s, the whole music industry was obsessed with digital perfection.
The DX7 era.
Yes, you had massive commercial hits being driven by synthesizers like the Yamaha DX7. Everyone wanted that pristine, glassy, polyphonic digital sound. So this gritty, primitive CMOS experimentation was just violently shoved to the margins of electronic music. No one wanted a synth that sounded like a struggling calculator when they could have a DX7.
Exactly. And throughout the 1990s, this approach survived only in heavily fragmented pockets. You had a few hardware hackers opening up children's toys to circuit bend them or, building little noise boxes in their garages, but there was no unified language or community.
The 2000s changed the landscape entirely, though. The internet gave these isolated garage hackers forums, personal websites, message boards, so they could finally share their circuit diagrams.
Yeah, that connectivity was huge.
And the term Lunetta Synth really solidified during this era. The movement exploded for one very practical reason. The parts cost practically nothing.
True.
You could walk into a local electronics store or go online and buy a handful of logic chips for pennies. The circuits were so wonderfully simple that you didn't need a degree in electrical engineering. You could buy a cheap soldering iron and build an instrument on your kitchen table in a single afternoon.
And that momentum carried directly into the 2010s, which saw a massive cultural reevaluation of hardware in general. This ran parallel to the global revival of modular synthesizers, those
Hmm.
massive walls of knobs, flashing lights, and tangled patch cables you see in electronic studios today.
Oh, yeah, they look like old telephone switchboards.
Exactly. The Lunetta community grew right alongside that modular boom, and it led to dedicated builder workshops and a really deep aesthetic appreciation for bare, exposed circuits.
Okay, let me push back on that for a second, though. I am picturing a board covered in messy wires, and you just mentioned modular synthesizers. I think you, listening to this, might be asking the exact same question I had when I was reading the source material.
All right, what's the question?
Isn't a Lunetta synth really just a poor man's modular synth? Like just a cheaper, grittier way to patch cables together?
It looks identical on the surface, I'll give you that. But the underlying language is completely alien. A lunetta is a fundamentally different instrument.
Really? How so?
So traditional modular synthesizers, whether it's a vintage Moog or a modern Euro rack system, they rely on a concept called control voltage, or CV. In a traditional modular synth, if you send 1 volt of electricity to an oscillator, it plays a specific pitch. If you smoothly turn a knob to send 2 volts, the pitch smoothly glides up to the next note.
Right, it's like a sliding scale.
It is a continuous, sloping ramp of information.
But Lunettas don't have smooth ramps.
They only understand binary cliffs, high or low, true or false, 5 volts or 0 volts. You cannot send a gentle sweeping voltage to a logic gate. It only knows on and off.
Wow.
Because it relies entirely on logic signals rather than continuous voltage, it requires a completely different approach to patching. It really is a separate evolutionary branch in the family tree of electronic music.
It's like finding a deep-sea creature that evolved in total isolation.
That's a really good way to put it.
So what does this all mean for us today? Let's bring this deep dive into the present moment. Why should you, the listener, care about this primitive, chaotic technology when you can download an app that generates a million perfect sounds for free?
This raises an important question, and I think the modern relevance breaks down into 3 distinct areas: music, education, and art.
Okay, let's start with music.
Musically, this CMOS approach has deep, undeniable roots in noise, industrial, and experimental genres. Those are musical cultures that fundamentally value the happy accident. They value the raw texture of sound and the physical friction of the machine over tight, gridlocked pop control.
And the educational aspect is just brilliant. Building a CMOS synth is an incredibly effective tactile way to learn electronics.
Oh, absolutely.
Because the chips are executing pure logic, you are visually and sonically learning how computer circuits actually think. You experience the physical principles of oscillation firsthand. You get this visceral, sometimes literally shocking direct relationship between raw electricity and the sound it makes. You aren't just dragging a block of code on a screen, you are feeling the circuit come alive in your hands.
And that physical, tactile connection leads directly into the third area, which is art. The circuits themselves frequently become visual installations. Because logic gates operate on simple on-off states, builders naturally pair the audio outputs with LEDs.
Oh, that makes so much sense. So every time that strict A&D bouncer opens the door to let a sound through, an LED flashes.
Yes.
When you build a complex Lunetta system, you get this beautiful, chaotic synchronization. You have these sputtering guttural sounds synchronized perfectly with flashing lights, all sitting on top of the raw industrial aesthetic of a board covered in a massive tangle of colorful jumper wires.
It's gorgeous in person.
It is basically a sculptural art installation where the messy wires literally are the canvas. It's this incredible cross-section of engineering, noise music, and visual art.
Which brings us to the philosophical core of why this matters. We live in a modern world that is ruthlessly optimized and perfectly controlled. We have software algorithms that can instantly fix a singer's pitch, quantize a drum beat so it lands perfectly on the mathematical grid, and generate any instrument imaginable without the artist ever having to touch a physical object.
Everything is sanded down.
Yeah.
It's too perfect. There's no friction anymore.
Exactly. CMOS synths represent the absolute polar opposite of that modern convenience. They are stubbornly inefficient. They are inherently uncontrollable.
Right.
They deliberately restore the unpredictability, the physical limitations, and the raw, frustrating friction that digital software has spent 30 years trying to eliminate. They remind us that sometimes friction is the exact place where art actually lives.
That is profound. To wrap up this deep dive, CMOS and Lunetta synths are so much more than just quirky DIY noise boxes for soldering nerds.
Oh, really are.
They are the physical artifacts of a subculture that literally turns cold, rigid math into breathing, chaotic music. They prove that imposing massive limitations on yourself, like forcing yourself to use only binary logic chips, abandoning smooth analog filters, and intentionally starving the voltage, can actually breed entirely new, bizarre forms of creativity.
By stripping away all the modern tools designed to make music easy, the builder is forced into a genuine, unpredictable dialogue with the machine, and the machine pushes back.
I want you to think about that in your own life. Sometimes having fewer tools, rougher tools, and frustrating constraints actually forces you to be infinitely more creative than you would be if you had a polished, perfect app that just does everything for you with one easy click.
Building on everything we've explored today, I'd like to leave you with a final thought.
Go for it.
We've seen how a perfectly engineered, hyper-optimized environment can actually stifle unpredictable creativity, and how injecting a little instability, a little voltage starvation brings the machine to life. Look at your own daily routines. What highly optimized, flawlessly scheduled, perfectly routine areas of your workflow might actually benefit from a little low-voltage chaos? Where could you intentionally introduce a constraint or starve the circuit just a little bit to see what beautiful, unexpected noise emerges?
I love that. We can all use a little low voltage chaos to break us out of the grid. So the next time you hear the pristine perfection of digital audio coming out of your phone, maybe take a second to appreciate the wild, untamed noise that those exact same microchips are capable of making when you let them off the leash. Thank you so much for joining us on this deep dive. We'll catch you on the next one.